Davisson and germer experiment. De Broglie hypothesis of matter waves was experimentally confirmed by Clinton Davisson and Lester Germer. So Davisson and Germer is a two different scientists in the year of 1927. Okay, they are doing an experiment in the de Broglie hypothesis. Okay, by analyzing the waves. So that they demonstrated that electrons beams are diffracted when they fall on the crystalline solids. Okay, so when the ray when it that falls on the some crystal means they can see some beams are diffracted, which is nothing but the electron beams are diffracted. Okay, so since the crystal can act as a three-dimensional diffraction grating for matter waves. So for the waves, the crystal can act as a three-dimensional diffraction. So the electrons waves incident on crystals are diffracted off in certain specific directions. So you can see the figure there. So that is the schematic representation of the apparatus for the experiment. So the filament F is heated by the low tension battery. So you can see the diagram very clearly. It's in your book, it's very clear. So this is the electron gun. Okay, so this is the electron gun and this is the aluminum diaphragm. So aluminum diaphragm, it used to um, uh, allow the electron in a straight line. For that reason only they have placed the aluminum diaphragm and this electron gun, and they have connected the F to the low tension battery, and this aluminum cylinder is connected to the high tension battery, and this is the incident ray. In this place we have small gap which allows the electron in a incident beam so that it falls on the nickel crystal. Okay, nickel sodium crystal. So this is the construction of the experiment. This is the setup of the Davisson and Germer experiment. Okay, so hope you don't have any doubts. Okay, so then okay, so now we'll read this. You can able to understand it clearly. The filament F is heated by a low tension battery and electrons are emitted from the hot filament by thermionic emission. So in the previous topic itself, we have studied what is thermionic emission. So thermal means heat. Okay. So where in by mode of heat, if the electrons are emitted means that is called thermionic emission. Okay, so they are then accelerated due to the potential difference between the filament and the anode aluminum cylinder. Okay, by a high tension battery. So electron beam is collimated by using the too thin aluminum diaphragm, and it's allowed to strike a single crystal of nickel. Okay, so directly the electron will incident on the nickel crystal because of that aluminum cylinder and the thin aluminum diaphragm. Okay, so the electrons scattered by the nickel atom in different direction are received by the electron detector. So the electron gun, so first we'll see what is electron gun. So in the electron gun means gun means it will produce the electrons. Okay, that electron gun will produce the electrons and it starts moving by means of thermionic emission. The electrons will come towards the thin aluminum diaphragm, then it reach the aluminum cylinder. So that aluminum cylinder is connected to the high tension battery. So now the electrons are come in a single thick line. Okay, it strikes the aluminum cylinder and it comes in this thin line, and that is called the incident beam. So now the incident beam is going to strike out the nickel crystal. So after it touches the nickel crystal, the beam will diffracted, okay, throughout the Around this nickel crystal, the beams are diffracted like this. Like this, it will diffract. Okay, so for to find out the electrons are scattered, I'm using the electron detector. By using of electron detector only, I can able to find out the waves that is produced by the electron. Okay, so now we'll read this. The electron detector which measures the intensity of the scattered electron beam. Okay, underline that line, intensity of the scattered electron beam. So the detector is rotatable. Okay, you can rotate this detector like this. Okay, whenever you vary the detector, the intensity of the beam also will vary. So the detector is rotatable in the plane of the paper so that the angle is phi between the incident beam and the scattered beam. So this incident beam and scatter beam. Okay, so can be changed at our will. So according to our own wish, we can rotate it and we can find out the angle between this scattered beam and incident beam. So the intensity of the scattered electron beam is measured as a function of the angle theta. So they have given you at 54 volt only, we will get the maximum intensity. Okay, if I give the potential difference of 54 volt, I will have the maximum intensity. So that is what they gave in your book. So shows the variation of the intensity of the scattered electrons with the angle theta for accelerating voltage of 54 volt. For a given accelerating voltage, the scattered wave shows a peak of maximum at an angle of 50 degree to the incident electron beam. So that is what I have told you now. Then this peak in intensity is attributed to the constructive interference of electron. So diffracted from various atomic layers of the target material. So from the known value of interplanar spacing of nickel, the wavelength of the electron wave has been experimentally calculated. Okay, so the wavelength can also be calculated from de Broglie relation for V is equal to 54 volt and the wavelength is 1.65 Armstrong. Okay, so just you apply the de Broglie wavelength formula. So lambda is equal to 12.27 divided by root V is the final formula we found out for the electron. De Broglie wavelength of electron, and this is that formula. Okay, this is that formula Armstrong. So you just apply the volt value. Okay, volt value, potential difference value in this. So you will be getting 1.67 Armstrong. So the value agrees well with the experimentally observed wavelength of the 1.65 Armstrong. Thus, this experiment directly verifies de Broglie's hypothesis of wave nature of moving particles. Okay, so the de Broglie hypothesis, the particle is moving in a the beam is moving in a wave. We know that light will behave as well as in wave as well as the particle. Okay, so here it behaves as a wave, but it is the moving particle. Okay, so that is the value is the wavelength is 1.65 Armstrong. That's all. Thank you.